Hello, I'm Esteban Quintero, and I'm going to be doing the control theory case study 2 for automated steering control system. So this is the original scenario. We have a automated steering control system, and it uses data about the vehicle's current position relative to the center lane. It's designed to steer the vehicle from the center of the current lane all the way to the adjacent lane when switching lanes. So first, we're going to start with our unity feedback model. This is for case A. As you can see here, we use our cascade form right there. And after plugging in our GC of S, AS, and GB of S, we end up with this closed loop transfer function of 0.6K over S squared plus S plus 0.6K. When we use varying proportional gains for this transfer function, we have proportional gains of 0.5, 0.75, 1, 2, and 3. The proportional gain I decided to go with is 0.75 due to its minimal overshoot but higher rise time and peak times and settling time over our 0.5. So our performance specifications. So is our open loop feedback model for steady state error. We have a step input and a resistance constant. So we're going to take the final value theorem right here. As the limit of S approaches 0, our Kp turns to infinity. We end up with 1 over, this should be 1 plus infinity on the denominator. And then when you have, of course, 1 over infinity, you end up with 0, so our steady state error is 0. We end up with a peak time of 7 seconds, rise time of 5.3 seconds, or 5.4 seconds, settling time of 8 seconds, and overshoot of roughly 3%. Also, we have a stable system because our poles are on the negative side, and we have an underdamped system as well. So this is the accelerometer feedback model for case B. We do our cascade forms and our block math down to here. Once we reduce all that, we end up with the resulting fourth order system right there. So with this system, with the fourth order system, can we do a second order approximation? Yes, because not only are our poles 5 sigma away, but our poles and zeros are also close enough to cancel each other out. We have poles located at -10.5 and zeros at -10 and 11. These poles and zeros cancel, and that leaves us with our dominant pole pair of -0.451 plus minus 0.459i. So performance specifications for this model. We can see the step response for our fourth order with our our selective K 0.75. For steady state error, we have the open loop transfer function right here. And as we go down, we can see that we have a pole at S equals 0, which gives us our type 1. We also have our unit input, our unit step function as well. So as we take the limit as S approaches 0 for Kp, that goes to infinity. Just like the last scenario, we have 1 over 1 plus infinity, which gives us our steady state error 0. Performance as far as it goes for performance characteristics, we have a peak time of 6 seconds, rise time of 4 seconds, and settling time of almost 9 seconds, and a 5.56% overshoot. We also have a stable system because we have our underdamped system and our poles are on the negative side. So design. So this is our case A and case B model right here. As we can see, our case B has the higher overshoot. Our case A has a faster peak, or has a slower peak time. And our case B has a faster rise time, but the settling time for case A is faster than case B. And then we can see our poles and zeros and our overshoot percentage. We can see that, of course, our overshoot is larger for case B. So final decision. Personally, I would go for case A. This is step response of just case A by itself. Because of the lower overshoot of case A, that means that there's less steering corrections, which means a smoother transition and a more comfortable ride. Lower overshoot also means a reduced control effort. That reduces wear and tear on the steering components. Of course, correcting back into the lane, that happens less. or at a less of a magnitude. The quicker settling time as well for case A allows the car to reach its desired final steady state faster, which is what we want when changing lanes. And then we do get a slower peak time and rise time, but it does mean that we do get a slower, more controlled transition from its current lane to the adjacent lane.